So Sebastian, are you ready?
Yes, I can hear you well. Thank you.
Okay, thanks. Okay, our next speaker is Sebastian Krumscheid. Sebastian is currently an assistant professor for uncertainty quantification at the Karlsruhe Institute of Technology. And previously, he was an assistant professor for mathematics for uncertainty quantification at RWTH Aachen University. And today he will talk about adaptive stratified sampling strategies for non-smooth problems. Please go ahead.
Thank you very much, Nadia. Thank you very much for this kind introduction. Maybe, okay, I don't know, I don't want to change my setting. I want to say hi. I want to actually show my face because it seems that you don't see my face. So let's deal with this for now. I also want to thank Raoul and AJ for organizing this workshop, and actually also to thank all of you for sticking around for the hybrid part. It's a pity that I couldn't travel to KAUST. I hope to remedy this, this soon. So what I want to talk to you about today is in particular some sampling strategies for non-smooth problems. And this is joint work with a colleague of mine, Per Pedersen, from the Norwegian Research Center. And in fact, it was Per who introduced me to the problem of this particular version of this non-smooth problems, because in their research group, they're working on this, what I call large-scale subsurface CO2 storage problems. So the idea really being that somehow you extract the CO2, you capture it, and you transfer it with some process really into the subsurface, and hopefully you trap it there long enough such that we can actually buy some time to, well, let's say solve climate change, or at least find some good ways of how to deal with it. And this is actually a real problem in the sense that also the international, well, intergovernmental panel for climate change has already identified this particular CO2 storage issue as one of the ways to kind of attack climate change in the sense of to complement the upcoming or the need to boost up renewable energies. As I said, so in this that's a real operational thing in the sense that, for example, I forgot the precise figures, but Germany is transferring money to Norway such that Norway is storing Germany's CO2 in this kind of subsurface areas, which are off the coast in the North Sea, such that Germany can kind of have a balanced CO2 level. Okay, so as I said before, that's kind of a complex process. You want to store the CO2, and you want to do this for very long time scales, such that we can actually, that we make sure it stays down there. Now, the problem that we want to investigate is really understanding, first of all, the forward uncertainty quantification part of this problem. So we want to quantify how do uncertainties propagate through these models. I wish I could show you some results on this particular problem. However, that's more for us at the moment, our starting point. I just want to indicate that this is an ongoing project. That's actually an international project with the lead in Norway at the Norwegian Research Center, where, so that's, for example, this currently used the storage area, which is called HORDA. They want to extend HORDA, and then this really requires a multidisciplinary approach on how to, including a systematic way of uncertainty quantification, such that we can ensure that the CO2 stays there, well, hopefully long enough. And you may see some kind of cooperational partners and then a few international institutions. So that's really an ongoing project. And part of this project is really to come up with good parameterization, with good characterizations of these uncertainties in these very complex models. Similar problems that may be of interest, where discontinuities may arise, is, for example, geothermal energy extraction. Just by looking at a picture for different fractured reservoir models, you already see that in this physical domain, you already expect some discontinuities. And then if you're adding some uncertainties on top of these models, it's not difficult to imagine that these uncertainties also propagate through the stochastic domain. So in essence, what we want to do is, what we want to attack here, the problem is we want to work on the following assumptions. So we observe that these simulation codes, either for this geothermal energy extraction, or if I'm going a slide back, for the subsurface CO2 storage problems, these are huge legacy codes. So some kind of container orchestration is out of the window because it's just nobody really dares to touch these legacy codes anymore. They have very complex geometries, layered materials, fractured materials, makes it extremely challenging. But on top of that, there's a bunch of uncertainties, right? Now, as I said before, in this ongoing project, what we're trying to do at the moment, we come up with suitable stochastic upscaling techniques to reduce the number of uncertainties, but there is certainly uncertainty, pun intended here. And unfortunately, these legacy codes are so complex, in particular for this fractured porous media application, that at least the practitioners we talk to, they don't want to allow for remeshing. It's simply too expensive, okay, because of the discontinuities. And in fact, when you combine these kind of flow or transport-like problems, where you expect to have discontinuities both in, let's say, some material properties, but also if you think about hyperbolic equations that develop discontinuities in the solution space, combined with uncertainties, there will also be discontinuities in the stochastic domain. So what this means is oftentimes you know there may be discontinuities, both in physical and stochastic domain, but you have no idea where they are. Okay, so that's the part, that's the tricky part. So in this talk, what I want to do is I want to, this will be a quite applied talk. I want to share with you some of our approaches and some of our ideas that we followed to attack these kind of problems, and share with you some ideas that worked and some of them that didn't work so well, just in the spirit of this workshop to give you some tools or some ideas what you could try in different or similar applications. Okay. So the setting is that we keep our assumptions to a bare minimum. We really want to do something about in the black box approach. So we have some model, it's our complex model. It's been fed some random input psi in my notation, as usually compute a quantity of interest Q. And again, typically I would be tempted to work in some kind of multi-level framework, but here the assumption is that remeshing is too expensive, so we have no control over the bias, or put differently, we simply say, hey, dear practitioner, please tune our model F in such a way that you trust its physics forecast, physics predictions. So we really have just this model F. Still, we want to compute, let's say, an expected value of some quantity of interest as accurate as we can for a fixed computational budget. Very simple, very common approach. Now, Shihab has already given a fantastic talk about the ideas of importance sampling, so I can be a bit brief here. But if you want to estimate expectations as accurate as possible under a certain budget constraint, then what we want to do compared to Monte Carlo is we want to reduce the variance. And there exist lots of different tools. I just clustered it in two approaches. One which I call sampling-based approaches, something like control variate or importance sampling. Now, in this setting, we couldn't think about a good control variate usually. And for the importance sampling, since we don't really know where the discontinuities are in the stochastic domain, we also didn't really, we had some ideas about importance sampling, but it didn't really work out for us. Similarly, if you think about some structural sampling ideas, like quasi-Monte Carlo, these methods, to be effective, we require regularity of our quantity of interest as a function of psi. And again, we work under the assumption that there may be some discontinuities even in the stochastic domain, so we don't want to really rely on smoothness. There do exist some spectral approaches for this, let's say, also for these problems, for these hyperbolic or random hyperbolic problems. So what they then do is typically they try to track the discontinuity, like you do, for example, in standard hyperbolic deterministic hyperbolic systems. So it's front tracking ideas, for example. And usually they have been developed for rather toy problems because they follow an intrusive approach. So again, for our legacy code, we have very little hope that these intrusive approaches will be possible. And as I said before, we have no idea about the location of our discontinuity. So when we then go back and look at this picture again, we realize, okay, discontinuities in space are typically resolved by having an adaptive mesh, right? Or very well, a mesh that is trying to resolve or getting close to resolving discontinuity. So the approach that we are following now is we want to do a stratification approach. So we're going to use stratified sampling as our variance reduction technique and try to tailor it to the unknown discontinuity. That's why here the outline is 2 parts. Judging that I'm already quite slow, I mean, we're going to start with part 1, obviously, where I'm talking about adaptive stratified sampling, tell you a little bit about our ideas on how to get to this one, and details are in this first part, in this first work. And then based on this first part on adaptive stratified sampling, we were trying to, I'm going to tell you some ideas that we had on how to combine stratified sampling with Latin Hypercube. But for this to make sense, let's get into some settings here. So again, we have our quantity of interest given as a function, evaluated some random input, some n-dimensional random input. For us, our setting is we assume that all components in our vector are independent, so that all dependency is hidden in this function f, and that we can scale each component to the unit cube. So our starting domain is the n-dimensional unit cube. And the idea of stratification is then very simple to tessellation in the PDE set, in the mesh discretization setting, that we simply split our unit cube now in a bunch of smaller domains. In this picture, it's also cubes. So and now each of those little domains, little subdomains, we're calling a stratum. So our entire domain is made of a bunch of strata. We have n strata of those, and they're disjoint. Okay. Good. And then this curly S is what I will call our stratification. So the collection of all of those little strata. Good. So then what is the stratified sampling estimator? It's a well-known variance reduction technique. So we now say we have to consider, or we're going to consider a random variable Qs, which is the restriction of our, or the restriction of our original quantity of interest Q, such that our input when psi lives in S. So it's a conditional distribution, which I've written down here. And now with this conditional distribution, we can now split our quantity of the expectation of our quantity of interest, which was the expectation of f under the distribution of psi, into the distribution of all the small strata. That's by law of total probability. Good. Now the idea of a stratified sampling estimator is now that in each stratum S, we're going to do a Monte Carlo estimator of this expectation here. So what we have to do then is we have to sample psi in each stratum. For us, it's a uniform distribution, evaluate f for the samples, and just do a Monte Carlo average. Okay, so that's our estimator here. We're sampling IID from our conditional distribution from QS. Now, in each stratum, now we have degree of freedom of how to decide how to choose our number of samples, NS. So the total number of samples, the total number of function evaluations we have to do is capital N, which is a sum of all the function evaluations or samples in each stratum. Good. So far, so good. Then we can also compute the variance of this estimator. Right, it's given here. It's a generic formula where now sigma S squared for me is the variance conditioned in the stratum S. Now, if you look into this formula, so it's the variance of f constrained to be in constrained to be in S. So if this variance is certainly minimal, if our stratification is such that the function f is almost constant in each stratum. That's the idea, right? So if we had, let's say, if this was our function f as a function of our one-dimensional variable psi, then the optimal allocation would be, hey, I simply take this as stratum 1 and this as stratum 2. And I would get the estimator with 2 strata that has minimal variance. Okay, of course, that's our intuition, but it's overly optimistic because this would require knowing us where the jump discontinuity is, which we do not. So the remedy, what we are hoping for in practice, is that maybe we can somehow, using samples, identify a stratification such that such as the jump discontinuity that may be there is isolated in a stratum of small size, right? Because the size PS is the size of our stratum. So if we can isolate our jump discontinuity or any sharp features in a strata of small size, then we are still in business. Okay, so that's really the analog of our PDE discretization, the mesh discretization, the mesh for this discontinuous or this fractured medium. Okay, so now that's the idea. The question we still have to answer is, how should we choose the number of samples in each stratum? And if you check the literature, there's a bunch of, well, there's actually two most popular approaches. One is the so-called proportional allocation, which is just to say that the number of samples in my current stratum S is chosen simply to be proportional to the total number of samples I'm willing to invest, and the proportionality is achieved by the size of each stratum. Okay, good. And then if I then use this particular formula for NS, I end up with a variance for the proportional allocation stratification estimator of this type. Now, on the other hand, there is this optimal allocation idea, where you're saying, okay, if I go one back, I look at this formula and I try to, now I'm looking at the constraint optimization problem of minimizing the variance subject to the constraint that the total number of samples is equal to capital N. If I'm solving this optimization problem, I get this particular choice for the number of samples, and this is the corresponding variance. And this is again, optimal allocation gives a lower one. Proportional allocation is an upper bound for optimal allocations variance, and that's a lower and variance. It's never increasing compared to a Monte Carlo estimator. Okay, it's bounded by Monte Carlo variance. The difficulty is, if you go for optimal allocation, which is optimal as the name suggests, so this is what we want to do. The number of samples on each stratum depend on the variance or the standard deviation inside each stratum, which we do not know usually. So this result is only useful if you knew the variances or the standard deviations in the stratum. And if you don't, then we are in a little bit of a pickle, in the sense that if you're now estimating this standard deviation sigma s, it could happen that if you're having, let's say, a piecewise constant function where gamma is now our the parameterization, the curve where our function jumps, and if we have too few samples that inside our stratum S all live on the same side of this jump discontinuity, then the variation is 0. So our estimator for sigma S would be 0. So we are drastically underestimating the variance, and this is of no use anymore. Okay, so that's really the difficulty here. So on the one hand, we have proportional allocation being quite robust. There's nothing that we have to do about the variance or standard deviation. On the other hand, we have something which is not very robust but optimal. And to what we are going to use is I'm going to show you the reason why. But what we are introducing, or what we have introduced, is so-called a hybrid allocation, where we're aiming to combine benefits from both worlds. So, which is just a convex combination of proportional allocation and optimal allocation. So we are introducing this parameter alpha being 0 simply gives us proportional allocation, alpha equal 1 gives us optimal allocation, and alpha in between is what we call the hybrid versions. Okay, so does it actually matter? So why do we do that? Well, let's have a look at a very, very, very simple, let me say it again, it's a toy problem, right? So we're looking in n dimension at a standard uniform Cartesian partition of our unit cube. So each stratum is now of the same size, 1 over n. And then we're computing a bound, then you can compute a bound for the variance of our stratified sampling estimator. And for fixed number of samples. So we're getting this bound, assuming that our function f is sufficiently smooth. Now, this bound is valid for any alpha. So from this argument, actually, asymptotically, let's say, if we're increasing the increasing the size of the stratification, alpha is not really that relevant, right? So hey, sure, we can make our stratification fine enough. Let's simply go with the proportional allocations because it's more robust. Now, if we look into the other borderline case, where we take the same stratification, but now our function f is assumed to be piecewise constant, that is jumping across a certain curve. So if we have one value here and a different value on the other side, and the difference in the function value is delta, then the situation changes. So then say if we're taking, so okay, this that's the number of strata we have in total, size of t, so t is a set of strata that contain our jump discontinuity, so this gray area here. And details are not important. What's important is the power to which this object is raised. So if you're taking proportional allocation, because that's a number that is smaller than 1, we get this ratio being raised to the power 1. While if we took optimal allocation, assuming we knew the variances, we get the same ratio raised to the power 2. Okay, so clearly we want to get to optimal allocation for this particular discontinuity. And but we still have in the back of our heads, it's not robust. So the interesting thing is that if we're getting into this range of alpha that is slightly smaller than 1, but sufficiently bigger than 0, we actually get up to a certain prefactor the same power on this ratio of the size of calligraphic T over the size of calligraphic S. Okay, so the hybrid allocation does have its perks in this particular setting. Okay, so now of course we want to, the title suggests I want to do adaptivity. What we eventually want to obtain is a stratification like this, right? This would be our dream come true. We have just a few samples, very few strata, and strata can be of different size. So let's talk about the adaptive procedure now. Okay, so again, I repeat myself here. We don't make any particular assumptions of f, other than we can evaluate it pointwise. And the idea to achieve adaptivity, and that's not new, that's actually quite common in the sampling procedures for discontinuous problem, is to do this batch-wise. So capital N is our total budget. And now instead of simply doing Monte Carlo or one stratified sampling at Monte Carlo, what we want to do is we are starting with a certain stratification, for example, just one stratum, use a batch with some of our budget to draw samples, and then by some kind of, then we somehow try to extract information about where we should split strata to refine our stratification, to something I'll try to illustrate here. The idea again is borrowed from this this adaptive meshing tools for PDEs, where you need an error indicator that tells you, hey, maybe you should refine your tessellation. Okay, so therefore the first constraint is that after we are refining our stratification, we want that our old stratum is being split into 2 new strata. And we keep doing that. And of course, somehow we need to decide how we're constructing our batches, so how we are splitting our total budget. And I'm not going to go into much details here, but we're going to scale the new samples. So given a certain sample that we have used already, we're adding a few more samples. We scale this by the size of our current stratification. And for the plots that I'm going to show you, I'm going to show this for a different value of C, but we do have some selection criteria for how one can do this in practice, just without having to do this multiple times. Okay, so we want to split things. This already implies some requirements. So for the implementation purposes, we want to keep it simple, right? That meaning that once we have a stratum, we split it. It would be convenient if the stratum that's split is being split into 2 strata of the same type. So splitting, of course, I could take a cube and I split it in a weird way that I don't have any cube anymore, or don't have 2 rectangles anymore. So that's why we are restricting ourselves to the same type of strata, which makes implementation easier. In each stratum, we need to sample QS. So we need fast sampling each stratum. So fast uniform sampling in each stratum S. This is a constraint, and we need to know the size of the stratum, the measure of the stratum is also done. So for these reasons, we're going to restrict our attention to hyperrectangles and simplices. Admittedly, we started with simplices because we thought from the, let's say, finite element methods, this is maybe gives us more flexibility. Turns out this is already quite good. Anyway, so we have both available. Now we can discuss how we should split these hyperrectangles that remain hyperrectangles. So in n dimensions, you have n possible candidates for splitting a hyperrectangle. You have a few more if you work with simplices, but we impose this kind of structured rules, always splitting according to some midpoint to get then two equally sized simplices or hyperrectangles out of the original strata. Okay, so now the question is, now we have a certain stratification. Let's say this guy, we have drawn some samples. Between each stratum, now we have a certain number of samples. If we then manage to identify where to split, we can split, assign the existing strata to where they belong, now under the split strata, and we distribute new samples according to our allocation rules. The question is that we're trying to answer is, where should we split, right? And to keep it simple, so we want to split in a way that using then the next batch of samples that we're adding to the existing ones, we want to get an estimate that has reduced variance. So we need we need an identifier for to show us where in which stratum we have high variance, because these are the ones that we want to split. And there exist a bunch of different techniques again. So we want to estimate the variance. So here I'm stating the variance formula again, now for the hybrid allocation already. And by looking into this formula, you already see that, well, changing a stratum, for example, if I take one stratum out of my stratification, I split it in a certain way, this has a non-local effect because of this weight here that comes in because of our hybrid allocation idea. It will affect all other strata. So that's slightly inconvenient. Nonetheless, for, let's say, complex problems, we can still do this kind of bookkeeping problem of a greedy optimization of this object. So what we're looking into, we're doing this kind of one strata at a time. This is the variance that we have for our current stratification S. Now we're computing the variance for our stratification, where out of the entire stratification, we take out one stratum T, and we split it across a certain direction J. And we want to find then the stratum and the direction that gives us the biggest variance reduction. Okay, so that's the whole greedy approach that we've used. And we can, of course, repeat this multiple times if needed. Okay, good. So let's have a look at this at an example. So we start very, very simple. Actually, let me go a few slides back because I forgot to highlight a point. I'm sorry for this. So let's go back to this lemma here, because what I want to highlight, and this is what we're going to see in the numeric examples as well, is sure, this is done for a very simple problem. But even this simple problem already, since it's kind of a domain decomposition idea, we are suffering the curse of dimensionality, right? So we're getting our rates deteriorating as our number of samples, as our dimension increases. So that's bad. So that's why we are only working with moderate dimensions. And talk about moderate for illustration purposes. Let's start with 2 dimensions. So we want to compute effectively probability that our uniform random variable is living inside some ball. And this ball is depending on our dimension and tweaked in a way that we get an expectation of 1/2. Okay. Now for case equal to 2, just first some iterations of this method. So we're using simplices. So that's kind of the iteration, how the process goes for a certain hybrid allocation rule and a certain constant C, right? So somehow, as you would expect, we have no idea where the discontinuity is, but the procedure is refining our domain, meaning we're putting more strata in regions where we are actually seeing some jump discontinuity, some jump. Okay, so now what we're going to plot, what we're going to compare is we're going to compare the variance. So the variance of our estimator, so the variance of Monte Carlo estimator, it's an unbiased estimator, versus the mean squared error of our estimator. So we're putting the mean squared error here because our method is only asymptotically unbiased, because we are using the next stratification, because we are using our current samples to inform the next estimator, and we're reusing those samples, so we are only asymptotically biased. That's why we can use mean squared errors, and we're plotting this for different sample sizes. So that's our total budget, and for different values of this coefficient C of how many more samples we're adding between batches. And I'm not going to discuss much the different values of C, but let's say for this and then these two pictures are for different values of alpha for the hyperrectangular stratification, and the other guys are for simplices. And what you see is that, I mean, they do fairly well, so we get some speed ups. Of course, since we are revealing the discontinuity as we go along, the more samples we can invest sampling, the more actually we use the variance, because the more we find we're getting, the more we find we're localizing the discontinuity. And yeah, these are repeated Monte Carlo ones. Okay, then of course we also looked into some other problems. This is, for example, one of the simplified CO2 storage problems, which is a two-phase flow. I will be quite shorty because I want to talk about the second part as well. But what's important here is that it's a simple, conservative almost conservation law, but our flux function f in this equation is now random. So we have some random background flow rate, we have a certain random mobility ratio, and we have a certain random permeability. So what our quantity of interest is, now we have these two phases of CO2 and brine, and we're interested in, so we're injecting it, we're letting the CO2 flow downstream, and so then we're measuring the plume height in this particular setting, 100 meters downstream, and whatever time units you use, so some 600 years after the end of simulation. So this is so it's not that easy to see, but what I want you to see is, so it's now in this particular simplified setting, it's three-dimensional in stochastic plane, and we also, in this simple hyperbolic system, we have discontinuities in the stochastic domain. Okay, so it's a PDE. We expect continuity in state space with respect to spatial variable, but you also have discontinuity with respect to the stochastic domain. And in this particular example, the hyperrectangular stratification did not work so well, so we get a variance reduction of a factor 10, while the simplices gave us a variance reduction factor of up to 100. Okay, so there may be some merits of using simplices. We looked into different examples, different toy problems, and got comparable, right? I'm skipping over those, and I have a first summary. So now this is what I want to convey here is that in these problems where you have very little control over the objective function and very little, you only can do sampling, the stratified sampling idea can still be used in moderate dimensions. By suitably splitting, we can reduce the variance reduction, and the idea really is we are learning from the samples where the discontinuity is, but we do not need to track this discontinuity in the equation. I talked about implementation quite a bit. That's saying that we used hyperrectangles and simplices. So if you want to play with this code, it's available in pip or on GitHub. And this was all, I mean, there we really saw a big difference of our allocation. What I did not talk about, there's a few theoretical properties that I'm skipping under the carpet here. For example, we still have our standard limit theorem that is valid, and we have some dynamic like continuation idea for the choice of our alpha value. So typically we're starting with a robust estimator to avoid missing discontinuities. So we're starting with alpha small, and then using asymptotic properties from the standard limit theorem, we are postulating a procedure to adaptively choose alpha. It's our hyperallocation range. Okay, but so that's completing part one. And the last 10 minutes or so, I want to talk about the main questions that, okay, that's all good. There's still some work that needs to be done, but how can we actually do better? So typically last time I spoke to some of you, the typical question is that, okay, now that you have if you do a few steps of this adaptation, why not use some more effective estimator in these strata? And that's kind of a very natural question, and it was not so clear to us how to do that, admittedly. So at some point we sat down and we thought about this a bit and came up with a certain approach that seems to have some potential, which I want to share with you. Okay, so let's recall we have the idea of our stratification estimator is to have this particular splitting here. So you're decomposing into the sum over contributions over expectations in each stratum times its size. Okay. We want to keep this, and that's just a sampling-based estimator, right? So we want to keep the simple structure here, but hopefully come up with a way to increase the efficiency. And the next logical variance reduction technique for us at some point was Latin Hypercube Sampling. Okay, now in order to use Latin Hypercube Sampling, I'm going to sketch this in a minute, we're going to restrict ourselves for simplicity to hyperrectangles. So every stratum now is a hyperrectangle. So then the idea of Latin Hypercube Sampling is very simple, similar to stratified sampling, but instead of stratifying the entire domain, so here's a sketch for 2 dimensions, what I'm doing is I'm only stratifying each marginal. So let's say if I have 2 dimension, psi1, psi2. Now I want to sample, let me count, 5 random variables, 5 samples. What I'm doing is I'm having my 5x5 grid uniform in this sense, but I'm only stratifying the marginals, meaning in each column here is just 1 sample. Okay. I do this for each marginal, so also in this direction I have only 1 sample. So that's this kind of special case of a stratified sampling in some sense, where I'm only stratifying marginals. But of course, this is very cool. I mean, there's just very few samples in this particular ball. Okay, and this is somehow argued to help alleviate the curse of dimensionality, but we're going to get to this point, I hope. Okay, now having these samples, so this Sudoku-like structure in our sampling, we use those samples and we compute using the samples, what I call the Latin Hypercube samples now. We still compute our average, and that's our estimate for our expectation, the Latin Hypercube sampling estimator. And now this guy here is being plugged in here, and we have our estimator in principle that combines stratifying the domain, and then in each stratum we're doing Latin Hypercube sampling. That was our idea. Okay. Now Latin Hypercube sampling is in principle fairly well understood. It's an unbiased estimator, so that's good. However, the Latin Hypercube samples are correlated in the sense that in order to satisfy the Sudoku-like structure, they cannot be samples cannot be independent. Right? So because we have this correlation in the samples, is also that if you look into the variance of your Latin Hypercube sampling, you're getting in comparison to Monte Carlo, you get this second term here, which will only give you a variance reduction under a certain structural condition on your function f. right? For example, if the function is monotonic in each argument, then this will certainly reduce the variance. But this is something we cannot guarantee. Nonetheless, asymptotically, if we take more and more samples, we will converge some Monte Carlo-like. And in fact, if our function f is very close to an additive function, so then we can see that here the effect. So here's this sample size. Then we simply get the best approximation in terms of our function f in comparison with our additive function. And this is the variance reduction here, right? So if this was an additive function, then we actually had variance of higher order terms, so only. Okay, so lots of appealing results. How can we use this now? So we want to use it adaptively still. And what we've done in the first part is we did adaptivity by sequentially sampling. Okay, let me say that again. So we used some batch. We had a stratification given, we used some samples, we changed our stratification using some variance indicators. Then we assign our samples to the new strata, and we're adding samples to an already existing strata now based on our sample allocation rule. This is no longer possible for Latin Hypercube sampling because the Latin Hypercube sampling, so the sample that we're getting, is not nested in the sense. So if I'm going back here, if I, for example, now here I'm producing 5 samples, if I want to produce 6 samples, I would get a partition. Would get a 6 by 6 grid here, and then all samples may not satisfy this this Latin Hypercube Sudoku structure anymore. Okay, so samples are not nested. Similarly, some quasi Monte Carlo or low discrepancy sequences in quasi Monte Carlo also are not nested. If we now want to do something about this one, well, we have to change our approach, and our viewpoint therefore was, instead of doing a sequential sampling, we're doing a sequential estimation. So we're still decomposing our total budget capital N into batches of smaller size, NL. So now we have L batches. In each batch, we're estimating based on a certain stratification. And now using this information, using this estimator, before computing the next batch of a size NL+1, we're trying to infer maybe information about what stratification we should be using. Okay, so that's the sequential estimation. The estimator otherwise are completely independent. The problem is, if you do that, then we can maybe find some information on how to refine the stratification is. So now we have a sequence of those estimators that are using this increasingly more refined stratification. The problem is that the last estimator in this sequence, which may have the most refined stratification, has only used NL samples, which is typically much smaller than N, right? Because we have taken our total budget N and decomposed it into smaller batches. So this would be inconvenient, because then we have kind of thrown away lots of sampling function evaluations. And now comes another embarrassing simple idea, is that, okay, but we do have the sequence of estimators. Why not simply average those estimators? And the idea really is that simple, that if you think about doing a Monte Carlo with a certain number of samples M1 and another Monte Carlo estimator with a certain number of samples M2, independent of each other, of course, by averaging those, you get one Monte Carlo of the size of sample size M1 plus M2. And so the idea here is the same. So if you have a bunch of estimators, all unbiased, then we could look into this weighted ensemble estimators. We're taking and we're trying to find those weights alpha L such that this estimator here has minimal variance. So it's a constraint optimization problem that you can solve again. So you can find this is optimal alpha values by combining this. And this gives us at least one approach to not waste samples that we have already computed at lower when we started our sequence of estimators, right? So they will still have will still contribute. Okay. How do we define? Now I'm very quick, that's why I'm showing you everything already. So now, since we're doing Latin Hypercube sampling, we typically will have rather few samples in each stratum. So we are going to construct some sort of a surrogate model. So here we are committing the crime. I said we don't want to exploit variability, but for estimating variances, we're constructing a generalized polynomial chaos type approximation based on our samples inside a stratum, from which we then can first of all construct local variances using the polynomial chaos coefficients. And we can also, which I'm not going to touch here, is find which are the subset of dimensions that are really, really important. And that's really, in terms of a Sobol decomposition, that's where we are heading at the moment, but that's still ongoing. Okay, what time is it? A few more minutes. Good, and by using this generalized polynomial chaos type surrogate, we can then extract variances. And as again, we can now look into, so we are postulating again a rule on how to split a stratum, so that we can find now an estimator. That's our combined estimator that uses stratified sampling, and in each stratum using Latin Hypercube sampling by modifying this total variance term, or this variance term here. Yeah, in a greedy way, very, very similar to what we've done in the first part. But we have the additional step to computing the polynomial chaos approximation. Okay, finally, some examples. So first example is a function that has a singularity in A in principle if delta was 0. So now we're regularizing. This should be xi, backslash xi. Sorry for that. So it's a regularized singularity, and that's a problem that has been used in some other works. That's why we are also going to cite it here. And we have different plots for different values of delta now for the regularization parameter. We're comparing now the variance of ours. The red ones is stratified sampling with Latin Hypercube sampling and GPC surrogates. So it's a mouthful. And so we compare this to doing Latin Hypercube sampling directly, or doing standard Monte Carlo directly. And what we're seeing is that somehow this method works quite nicely in this simple example. Admittedly, that's a smooth function. GPC is all well established, right? It's a differentiable function. It's not. Oh, actually, maybe I'm missing a square here as well. Okay, and we get this kind of, in the eyeball metric, 1 over n squared variance reduction. And here's some snapshots on what the algorithm, what the procedure reveals. So it's now, this is for one value of delta, that's for a different value of delta, and that's yet for another value of delta. Delta getting smaller from the top to the bottom, and going from left to right, we have a different number of different size of stratifications. And what we see is in all cases, sure, this is maybe not so really suited for this because it doesn't have too much localized features. But here we nicely see that this procedure concentrates on the discontinuous, or on the sharp feature, which is still continuous but just very high gradients. Also notice that the share of sharp feature is not aligned with our stratification, right? Okay, then we're going back to our simple problem that we also looked into in the first part. So computing again the probability that some norm of our okay, here's a few typos. Sorry, so the norm of our random variable squared is in some, or that our random variable xi is in some ball of a certain radius. This tuning parameter is Cn is selected as the size of or depends on the number of random variables, and is tuned such that the expectations or the probability is equal to 50%. And now we're adding another parameter d here. So what we want to do is we want to study that, for example, the entire problem could be n-dimensional, but the discontinuity is only living in a d-dimensional subspace. Okay. So then, for example, if you're looking at this 2-dimensional problem, where also the full norm squared, for the full sum over all elements is here. We see this similar qualitatively same behavior as before. And what we're doing the next plot is now we're having a 3-dimensional random input, but the discontinuity is only in a 2-dimensional subspace. And then similar here, we have a 10-dimensional random input, but only 2-dimensional dimension of the discontinuity in 2-dimensional space. Okay, this looks all very nice, but okay, here's some pictures. Again, we are isolating on this discontinuity, and we see that even nicely half spaces are completely left untouched. But there's still a lot of work that needs to be done. For example, if you're going to a discontinuity living in a 3-dimensional space, sure, we're not doing worse Latin Hypercube sampling or standard Monte Carlo, but we don't really see the benefit as before. So that's still some. I decided to share this not so exciting result with you because I think that's what one should do. That there's still some work that needs to be done in this direction. And this brings me to the final slide, namely a summary for the second part. That so our motivation was, can we combine stratified sampling with some kind of design-based sampling estimators? Here, focusing on Latin Hypercube sampling. In principle, it's wasn't so direct in our approach, and the idea really was to use the sequential estimating strategies by weighted averages, but as I showed you in the very last experiment, there's still some analysis that needs to be done. And with that, I stop here and thank you for your attention.
Thank you, Sebastian, for a nice talk. Let's see if we have questions from the audience. Okay, we have one.
Thank you for the very nice talk. I have one question. So if you compare with this isotropic refinement, how much the algorithm will have the performance gain?
Yeah, let me okay. I thought I showed my face, so let's share my screen again. I suspect you're referring to the to this one.
Yes, that you have all the squares in this mesh.
Yeah.
So I wonder, I mean, comparing with this isotropic refinement with the one that you consider this, you can have this kind of rectangular meshes. I mean, what is the performance gain that you can achieve?
What we're hoping for is the following: that so let's be optimist. Okay, let me go to the numeric examples because then there's a concrete tessellation. Maybe you can see it here also. So by stratified sampling, we have. Sorry for jumping back and forth. Let me remind you what we're doing here. So if you go into stratified sampling, the first observation is that we need to decide how many samples we're using in each stratum. Okay, let's suppose for now that we're doing proportional allocation. Then the number of samples in each stratum is simply proportional to its size. Okay, so if, let's say, I magically came up with this particular stratification, then that's a relatively big stratum. But if, okay, this is not a good example. Let me refine my example. If it then, okay, because they are, okay, once at a time. So then, of course, we would also use relatively many samples in this particular region, although our indicator says, hey, the function is almost constant there, right? So you don't need to sample there. That's why we actually want to go to optimal allocation, because there the samples choice is not only depending on the size, but also on the local variance. Meaning, when we have a total budget of a certain number of samples n, and if I've identified this region where I have very little variance, so then the number of samples that I'm putting into this stratum from my overall budget is a small number. So I have much more samples left over to distribute them in the other regions, which may contain more information. So the only motivation for this, let's say, non-uniform discrete or tessellation is that we are going to get more information, or that we're going to draw more samples in regions where we actually have variability of our function. Does this make sense?
Sorry, I thought I was asking a different question. So I was asking about the refinement, that either you can do it like isotropic, that is, I mean, you refine it in each direction, or you can only refine it by, as you mentioned in your slides, that you're refining it in two similar structures.
Okay. So, okay, first of all, we're not always refining in the same direction, right? So we're checking all directions. So we have a stratum, we take a direction, we split, we check how the variance would change without drawing new samples, and then we make a decision. Now, so it's not always the same direction, that's important. And the second is, we want to remain in the same class of kind of strata. So for example, we don't want our, let's say in this picture, our cube to be split into simplices, because this would be a mess to implement in terms of connectivity list and so on. So it's more like a practical assumption.
Okay, so how important it is to consider this splitting like direction?
The direction you mean, but stay
that you
hyperrectangles,
consider-
for example, those three directions you mean?
Yeah.
Well, this is difficult to answer in generality. Because you could somehow construct examples where one of them would almost perfectly align with a jump to discontinuity or any sharp feature. And then, of course, this particular splitting would be beneficial over the other ones. So by checking different directions, we allow ourselves to well, better resolve the discontinuity or the sharp features.
Okay, thank you.
Do you have other questions? So if not, let's thank again Sebastian.
Thank you.
And we resume at 4. We have 30